So today we have speakers from Stanford University focused on a new way of treating wastewater. And we also have with us the general manager of Silicon Valley Clean Water, who is the host facility for some of these projects that are going on at Stanford. Bob Whitley and I have heard these presentations and became very excited about what they suggest in terms of the possibilities on treating wastewater, entirely different than what we were used to in terms of just relying on biological treatment. So with that, I'll turn it over to Bob. Thanks, Bob.
Good morning, everyone. So as Gary's indicated, our speaker today are Professor Craig Criddle, followed by Sebastian Tillmans, and we'll follow up with Teresa. And so this program is probably different than the times because it is new and exciting information. We're not bogged down by COVID. We're not bogged down by the politics. And it offers a new way of thinking about how we go about wastewater treatment. And to do that, put that in perspective, when I graduated from college, I was well educated in aerobic treatment of wastewater, known as activated sludge. That was my education, and it became big part of my career. So for 50 years, aerobic treatment, biological treatment, has been the linchpin of wastewater treatment throughout the state, the region, and the nation. There have been variations. There's been some modifications. There's been some efforts on efficiency, but in every case, aerobic treatment is a major energy consumer in wastewater treatment. So also to put that in perspective, when I graduated college, the price of oil was hovering below $5 a barrel. And oil and energy was reliable and pretty constant. There weren't any concerns about energy at that point. And so as we went about aerobic treatment processes, if we needed more horsepower, we added it. The only consideration was, are we going to how we treat the waste? Well, today, the price of oil is $94 a barrel. And depending upon what Putin does, it is going to either spike up or it's going to drop down a little bit. But it's still much higher, and therefore the value of energy is essentially important in any of the engineering and operations programs that we undertake today. So with that in mind, pay attention to what the program is, and then we'll come back. And format will be each of the speakers will have their turn in speaking in order. And then at the end, after Teresa concludes with her comments, then we'll open up to questions and answers. And you can either write them down in the chat room or raise your hand, and Lindy or I will try to monitor it and get through this. But please keep an open mind, because this is a different way of thinking about what we do. And it's got a long ways to go, but it is exciting. So with that, Professor Criddle, we kick it off, please.
All right, so yeah, I'm excited to be able to talk a little bit about new technologies that we're thinking about and working on at Codiga Resource Recovery Center at Stanford. And we've had some nice attention over the last couple of years, like the Brave Blue World. They talked about the Codiga Center and the technologies that were being hooked up and tested there, offering students real world experiences. This is just showing some of the things that we've been working on. So there's the Fluence membrane aerated bioreactor system. There's been testing of soil column testing of trace gas, of trace contaminants on turf grass, and now we're beginning testing of the micromedia filtration system. And of course, we've done some things with Google. There's a lot going on, and we've had a lot of interesting outcomes from that. So we're recognizing that there's more resources that we can recover from wastewater. I didn't put it on this slide, but one that's really turning out to be important now is information as a resource that's being recovered. Ali Bain has been doing amazing work on tracking SARS-CoV-2, basically keeping track of what's happening there with the pandemic. And we're able to monitor, it turns out, very effectively from wastewater, what's happening in the waste. Now, I want to now focus more on the material, the products that we can potentially produce from the wastewater. And besides the useful information, one, of course, is energy. It's an important target. And so these water recovery, water reuse are really big drivers for change. As you all know, there's a kind of a push right now in terms of aging infrastructure, climate change, needs for nitrogen and phosphorus controls, and safe residuals management, trace contaminants. So that's the push. And the pull is that there's really a lot of new things being tested and that are working and looking promising. I'll talk a little bit briefly about anaerobic secondary. I think Sebastian's going to talk more about that later. And then these other technologies that are starting to look promising. If we look at wastewater, just in terms of its resource value, I sometimes show this slide just to illustrate about how much what the most valuable product is from the water, which is the wastewater, which is the clean water itself, the tap water. And you can see that it's really about $1 per cubic meter, depending upon conditions in the market at the time. And but if you were to put it all in little bottles like that, it would be worth a lot more. So it's just interesting that there's these differences in just how you package things and the value of the materials that you're interested in. And there's also then the organic component. How much could that be worth? And we can do the calculation and figure out how much it's worth roughly. The energy in 300 grams of organic matter, which you would find in a cubic meter of wastewater. And you can see here the kinds of numbers we see when you look at all combustion of all the organics, it's 1.6 kilowatt hours. If you look at just biodegradable organics, it's 1.2. So
Hey,
that's
Greg,
it. Yes.
Greg, yeah, this is Gary. So I don't think your slides are advancing, and you're not on slideshow, at least on my computer. So it's kind of hard to see.
Yeah.
Oh.
There it is.
Okay, so this is what I was just talking about, the energy that's potentially latent energy that's potentially available within the wastewater. And
there we go.
You can see it now. I'm so sorry. I selected the wrong window, I guess, to share.
No problem.
Anyway, currently we basically recover energy only from the particulate organics right now when we do anaerobic digestion, but there's more energy available. And right now we're currently using energy for the soluble and colloidal organics. We require energy. So the net result is we have net energy consumption right now of about 0.4 to 0.6 kilowatt hour per cubic meter. And so how can we get the energy from this colloidal and dissolved organic matter rather than spending a lot of energy to get rid of it? And one way to think about it is in terms of methanogenesis and combustion of the methane that's produced. And we have good news on that front to talk about. I'll be excited to mention it, and then I'm sure Sebastian will follow up well. And the other thing that we're working on is a microbial battery, and we've got a potential party in India that's interested in this. So we're interested in using these microbial batteries to remove soluble and colloidal material. A microbial battery would be direct to electricity as opposed to going through a methane intermediate. Okay. Now, what might be possible then is that we could have a situation where we can go anaerobic on the anaerobic side, and just looking at what could be done, we could get water for agriculture from that. This would be replacing aerobic secondary treatment. And so it's very exciting, a possibility here that by doing that, we could recover almost twice as much biogas from the waste organic matter. And that would enable a significant energy production, net energy production in theory. But now we have something new to report that it's not just in theory. It looks like it can actually be done. Now, if we get additional energy from the wastewater, we can then potentially use that energy for power, but also for heat. And if it's used to dry the biosolids, we've done calculations that show that it could enable then even additional energy because of the potential for gasification and use of the syngas for additional energy. So we end up with, finally, at the end of the day, a very teeny amount of ash being produced from the process, so almost nothing for hauling. And we end up with an electricity benefit. And also, yeah, basically those two, the big ones. So is heat our friend? That's a question we could ask. In this case, we can make use of the heat potentially to dry the biosolids that are much fewer biosolids if we don't have aerobic process to deal with. So this process that we've been testing, and I think many of you have heard about, the anaerobic secondary treatment, the SAF-MBR 1.0 was first tested in South Korea. And this is the team of people that worked on that. You might all recognize the man in the middle there, Perry McCarty. So he was there working on it. And behind him, there's Chung-Hyung Shin. Now, Chung-Hyung has been, we've recruited him, and he's now at Stanford, helping to run the systems there, and also been working at Silicon Valley Clean Water. Now, what we've been initially start with was staged anaerobic fluidized bed membrane bioreactor. We call it SAF-MBR 1.0. What made it great about that was that it was able to meet US regulatory standards in terms of water quality. That was good. But the problem was that there was particle sparging that we were using to clean the membranes, and that caused some damage to those membranes. And so that was a problem that we had to address. And so at Kodiga Center, we replaced the particle sparging with gas bubble sparging, using biogas to sparge the membranes and clean them. And this was an important step forward for us, because now we weren't causing that damage. And the result of this, we've just published in Water Research, and basically now we can boast, I guess, that we have net energy positive production at the Kodiga Center. And so the energy balance, I'll just read this bottom line here. Energy balance on the SAF-MBR 2.0 indicated net energy positive operation with energy recovery from produced methane and exceeding the energy consumption due to the GAC fluidization and gas sparging. So we have net energy production. To our knowledge, this is the first time that this has been reported. We've thought it was possible, technically possible. Now we have evidence that it actually is possible. And then this graph is illustrating the production side of the equation there. And now we've been working at Silicon Valley Clean Water, and Sebastian, I think, will be saying more about this, but this is just showing the stages of construction. This system was different, unlike the one at Kodiga, where we use steel to build the fluidized bed reactors and all the system there. Here we're using concrete, and then there were many challenges associated with this new design, but basically the efficiency of removal has been very good for COD removal from this system, and I'm going to let Sebastian elaborate further on that rather than go through it now. And it looks like there are ways in which it might be integrated into the system in the future to think about how can we move this to a larger scale. We eventually would like to be able to replace much of the existing infrastructure that is necessary because of the aerobic systems we've used in the past, and then now replace it with anaerobic secondary systems. Of course, more testing is needed, but we have positive results from the both Kodiga and from Redwood City in terms of energy production. And this is just showing our way of thinking about how we're moving up the scale for a SAF-MBR. So if we look at the value of water and organics, we can, from a little table here, we can estimate what kind of energy value we can get in terms of revenue. And of course, water, the big winner, but organics also right there. What else can we do? There's other valuable materials and products that can be made from the wastewater resources. One is to think about stranded methane. What could we do with that? And then there's single cell protein. I'm just going to name a few things here. We've just published a paper in Nature Sustainability on the capacity to recover single cell protein from methanotrophs that are generated from taking the biogas and then adding air and getting the conditions right where we can get high density protein production. So we're excited about that. And that one is, there's some efforts going on to see if we can get something going in Bangladesh there. Okay, I'm gonna jump ahead. I'm a little worried about giving Sebastian more time here, but one more thing I want to mention that's kind of exciting to me is we were able to publish an article in Green Chemistry on a fire retardant, a wonderful fire retardant we can get from wastewater. And it's, guess what it is? It's struvite, which normally we think of as something, a nuisance in many cases, and that the fertilizer value isn't as good as we would like to see. But it turns out that a colleague, Eric Apple here, shown here, and his group in material science at Stanford, they've done testing, and we worked with them, and they did testing of struvite as a component of a fire retardant, and it looked very effective in that capacity. The struvite was as effective as the phosphate source that is commonly used in these fire control or fire retardant formulations. So the LC95A is shown here on the right is shown to be basically the same as the struvite in terms of its performance as a fire retardant, which means the beautiful thing about this is this means that we have a higher value product from struvite than we've ever imagined that we had. And so I'll just read this last thing down here. Struvite-based formulation exhibited performance comparable to the polyphosphate retardant, while requiring 60% less total phosphorus. Moreover, because the struvites derived from wastewater, applications of struvite in fire retardants can offset demand for mined phosphorus, a finite resource. Analysis of supply and demand for the conventional fire retardants in the US indicates that wastewater treatment plants could produce sufficient amounts of struvite-based fire retardants to meet US demands for wildfire suppression, while significantly improving revenues over direct struvite fertilizer sales. So I'm just going to end there because I want to give Sebastian the floor, but you can see that this is another exciting outcome that's come up recently, and I'm anxious to get the word out about what's possible with struvite. So that's all. I'm going to stop there and make sure that Sebastian has time. I don't know if there's questions, if there's time for that, I would be happy to entertain them.
So do we have Sebastian on the line?
Yes, I'm here.
And tell us where is here, Sebastian?
Oh, I am currently in the middle of the Austrian Alps, and it's been snowing. It's been snowing all day, and there's definitely not a drought where I'm sitting right here. I wish I could share some of our snowpack with California. Yeah. In the interim, it made for a great. I taught my 3-year-old son. Well, I didn't teach him because he's not yet there, but I showed him how to throw some snowballs against the window earlier today.
Cool.
But I will follow up on Craig's presentation and talk much more specifically about a local project that we've been doing in very close collaboration with Silicon Valley Clean Water. So I'm going to go ahead and share my screen. Now the big question is always, which screen can you see? Because I've got my, can you see the presenter view, or can you see the one that you're supposed to see?
I think we're seeing the one we're supposed to see.
Yeah.
Okay, great. So the project that I'm going to talk to you about today is a project that we've done with the California Energy Commission and with Silicon Valley Clean Water. So it's a project that I have to say the East Bay Leadership Council has had a really big hand in fostering, because when we had first pitched this project to the California Energy Commission, they unfortunately misunderstood what we were proposing to do. And we were able to come to a meeting of the East Bay Leadership Council and speak with the commissioner of the California Energy Commission to clarify. And I think that's one of the main reasons we were able to get a second opportunity to write a proposal to the California Energy Commission and get this project funded. So we're very grateful for the support that you provided to us early on. But this project is a project to maximize energy recovery from a new anaerobic wastewater treatment technology that that Craig already alluded to a little bit. So I'll jump straight into talking, and Bob teed it up as well, actually, by talking about the issues with aerobic treatment. But so why have we been interested in working with an anaerobic wastewater treatment system as opposed to the conventional way to do things? Well,
please.
Sorry?
I think that was an error. Go ahead, Sebastian.
Okay. So if you look at, I've got two kind of simplified process flow schematics here for a wastewater treatment plant. If you look on the top, it's a conventional wastewater treatment system. You start with primary treatment, where we remove as much of the suspended solids as we can to be able to send those to anaerobic digestion. But a lot of the organic material flows through to our aerobic secondary treatment system, where we have to invest a lot of energy to aerate the wastewater to be able to remove those contaminants. We can get some of that energy back because we can send some of the solids that are generated in the aerobic treatment back to the anaerobic digester, but we do consume it and end up consuming a lot of energy to facilitate this process. So an alternative would be an anaerobic treatment process, where we would have a primary treatment system. We would still send as much of the solids as we could to anaerobic digestion. But then instead of having an aerobic secondary treatment system, we would rely on an anaerobic secondary treatment. So we eliminate that energy consumption to then achieve a couple primary benefits. So first, we have less energy consumption, less electricity consumption, hopefully higher quality water, which we can talk about, I'll talk about in a bit, reduced greenhouse gas emissions from both the electricity and from some emissions that come from the wastewater treatment system itself. And then complementary benefits, because we're doing more anaerobic treatment, we're actually producing more methane gas that would translate to more renewable energy. We could be able to achieve this in a smaller footprint, and we would reduce the amount of solids that have to be hauled off site. So now putting that in terms of the operating cost of a typical wastewater treatment plant, these are some very generic numbers. Every wastewater treatment plant is different, but there's some broad, consistent elements here where a large chunk of the cost of a wastewater treatment plant are locked up in their electricity and their solids handling, their sludge transport and disposal. So if you had an anaerobic treatment system, you nominally could eliminate the energy usage, and you could also reduce the solids production, say by as much as 2/3. So the total savings in your operational costs would be on the order of about 36%. So you could, just based on this pie chart, an anaerobic treatment system, you should be able to reduce operating costs of the treatment plant by about 1/3, which is enough to motivate me for sure. So now to talk to you about the system, the process that we've been working on is called the staged anaerobic fluidized-bed membrane bioreactor. And like all good engineers, we've come up with an acronym for that. So we call it the SAF-MBR. It's a two-stage process. The first stage is a fluidized-bed reactor. What that contains is these little black dots here symbolize grains of granular activated carbon, which is the same material that's typically in a Brita filter, for example, if you have a household water purifier. There, it's typically used to absorb chemicals. In this case, we use it as a media on which bacteria can grow. So the bacteria form a film, a biofilm on these individual grains of carbon. And we push water, we recirculate water that flows vertically up through the reactor column, and it suspends or fluidizes those grains of carbon so that they're falling as fast as they're getting pushed up by the water, and they end up kind of sloshing around in the turbulence of the reactor. So that allows us to get really good mixing, really good contact between the wastewater and the bacteria. But because the bacteria are held on in these grains of carbon that are staying inside the reactor, we're able to hold on to them while we push the water through pretty fast. So that's the first stage, is the fluidized bed reactor. The second stage is a membrane tank, which these membranes have been developed by, there's a lot of different companies that furnish them now. The membranes that we've used are called ultrafiltration membranes. So they have a porosity of about 0.04 microns. To put that into perspective, typical bacteria are about half a micron. So this is the porosity is about 1/10 the size of typical bacteria. So it's a very, very fine filter that's there to retain all of the remaining suspended solid particulates in the wastewater, to enable them to basically marinate and stew in the reactor long enough to be able to dissolve, hydrolyze, and then be consumed by the bacteria that are hanging out on the carbon. So we have a recirculation pump that's fluidizing the carbon, but we also have a recycle pump that pumps the retained solids from the membrane tank back into the bioreactor to enable the bacteria to get multiple passes on those organics. So the system produces biogas because it's anaerobic. So instead of burning the organic material into carbon dioxide, we're transforming it into methane gas, which bubbles, most of it bubbles right out of the water. So we have a surplus, but we also recycle some biogas. We blow biogas into the base of the membrane to agitate the membrane, shake them, knock off particulates to keep the membranes clean. So when you think about the energy consumption of this system, it's the big consumers are in this recirculation pump that's used to keep the fluidized bed, to keep the carbon suspended, and also in the blower that's used. Now, looking at how this system could fit into a typical treatment plant system, Craig showed this slide briefly. I'll show it to you in a little bit more detail. This is a more generic wastewater treatment plant process schematic. Your water comes in, you have your pump station, your pre-treatment with your bar screens, primary clarifier, your secondary treatment system, filtration and chlorination before you can do discharge. In the case of the SAF-MBR, you could replace the aeration basin with the SAF-MBR system. And that would eliminate the need for the secondary clarifier. It would also eliminate the need for the filters, the sand filters, the dual media filtration that comes after. So you could you could eliminate, of course, recycling of the activated sludge. So your effluent from this system could go nominally directly to your disinfection process. We'll talk about, I'll introduce some caveats later. You would have a lot less waste activated sludge that would be sent to your digestion system. So this is kind of your big advantages of this system. There is no free lunch. So there are some elements that we still need to operate and manage, including some water pumps, the gas sparging blower that I talked about. And the new complexity in operating this kind of system is to manage the membranes properly. Now to talk about the demonstration system that we installed at Silicon Valley Clean Water. I included a process flow schematic for that as well. So we take wastewater from Silicon Valley Clean Water, and we can take either their primary influent or their primary effluent. And then from that, we can move that water through a microscreen, which is it's an alternative process to a conventional primary clarifier that works in a much smaller footprint. So we have that option at our demonstration facility to push the water through the microscreen, but we can also bypass the microscreen and go directly to a feed tank from which we feed the water into the recirculation loop, the fluidizing loop of the fluidized bed reactor. Water from there flows into the membrane tank, and it's pulled out of the membrane tank by a permeate pump through. So it's sucked through the membranes by a pump that sends it to our effluent tank. We have a biogas sparging blower that blows biogas from the headspace of the bioreactor into the base of the membranes, and then that biogas can flow back to the headspace to equalize. And then we have our recycle pump that pumps the retained solids from the membrane tank back into the biological tank. And then the excess biogas is stored in a biogas storage tank to equalize it. And then for this demonstration, we flare off the biogas that we produce. But of course, in a full-scale system, what you would want to do is take that biogas and use it beneficially. So you could produce energy from it, or there's some cool other technologies that are also being demonstrated at SVCW, like Mango Materials, where you could make biodegradable plastics or other things that Craig talked about. So now some pictures. We have our fully operational system at Silicon Valley Clean Water that is running at about 24,000 gallons a day. And so this is what it looks like. So that fluidized-bed reactor that I was talking to you about is this concrete tower that you see here. The inside dimensions of that concrete tower are 6 feet by 6 feet by 20 feet tall. So of course, when you factor in the concrete thickness, the outside dimensions are a little bit bigger. But we built it out of concrete because if we were to build a 12 million gallon a day plant, which is what SVCW is on an average on a dry weather day, you'd be building it out of concrete. That would make the most sense. It would be the most economical, and a form factor, a rectangular form factor like that is what would make sense. Looking at the same system from the other side, this PVC tank is our membrane tank. In there, we've got 9 membrane modules. This stainless steel panel is our control panel, and we've got a couple of pumps and blowers, etc., on the skid. So this system has been operating now for, it's actually been operating for longer than the slide I'm going to show you, but the data that I'm sharing for you right here is from the first 240 days of operation, and shows the startup of the system. So we started the system up, and there's a few different things going on this graph, so I'll walk you through it slowly. The lines that you see are the hydraulic retention time. Those tie back to the right-hand axis here. We started the system up at a hydraulic retention time of a little bit over 20 hours. And then we gradually pushed the flow rate up, which reduces the hydraulic retention time in the system, until we reached a hydraulic retention time of about 5 hours. The brown dots are the influent COD, chemical oxygen demand, which is a key metric of organic contamination in the wastewater. And the blue dots are our effluent concentration of COD. So you can see during our startup, our effluent concentrations were about 100 milligrams per liter. And then they actually the effluent concentrations came down even as we were ramping up the flow. So that's a really exciting performance from our perspective. And now to focus in on our steady state operation at our highest flow rate, or our design flow rate, 5 hours of hydraulic retention time. We were seeing an influent COD of about 550 milligrams per liter. And we were achieving an effluent COD of about 35 milligrams per liter average, which is compliant with United States secondary effluent standards for COD. And is about a 94% removal. So these are, we think, really, really good performance. To put it also in terms of BOD, which is a metric that's more typically on permits, we had an effluent BOD of about 15 milligrams per liter typically, which would also be typically in compliance with permit standards. All the while at 5 hours of hydraulic retention time. Oh, and our effluent suspended solids were 1 milligram per liter, which is what you would expect because that's a membrane bioreactor. So if we had anything higher than that, we'd be worried. But we achieved all that at about a 5 hour hydraulic retention time, which is lower than you can typically do with an aerobic secondary treatment process. So a conventional aerobic process would take about 7 to 10 hours of hydraulic retention time when you factor in both the aeration basin and the secondary clarifier. So hydraulic retention time directly translates into footprint. So the big punchline here is that this system shows we could achieve really high effluent quality anaerobically in a smaller footprint than you could in a typical aerobic process. Now, the other really exciting piece of this is biosolids production. So, and here I have to apologize. My units here are metric units, and I operate the Kotiga Center, and so my brain is constantly switching back and forth between the metric units of academic journals and the US units that are used in operations. And these graphs are in metric. But luckily here we're talking about biosolids production. So, grams of volatile suspended solids per gram of BOCOD that's removed. You could just swap in pounds and it'll be the same. But the system produced about 0.023 grams of suspended solids of VSS per gram of COD that was removed. When you compare that to a conventional activated sludge process, we're talking about close to a 90% reduction in the secondary solids that are produced. So you still have to process, you still have all your primary solids. So it's not a 90% reduction in the total solids that are produced, but still, when you're just looking at your biological process, this is a major reduction in your solids production, and therefore in the amount of solids that you'd have to haul offsite. Translating footprint into kind of visible terms at a wastewater treatment plant near you. This is an aerial view of Silicon Valley clean water. So based on kind of just quick and dirty visualization, this highlighted area here in blue is the aeration basin at SVCW. So the SAF-MBR biological treatment process would readily fit within that same footprint because we can achieve treatment in a lower hydraulic retention time than what's needed for an aerobic process. We can say conservatively, we would maybe take a little bit of the footprint of the secondary clarifier and for associated infrastructure, but that means that the rest of the secondary clarifiers and all of the trickling filters at SVCW would no longer be needed to achieve secondary effluent standards at that plant. You also would not need the dual media filtration system, so you can gray that space out as well. And since you're reducing solids production, you're reducing secondary solids by 90%. We estimate that you'd reduce your total solids production by at least a third once you factor in the primary solids, which means that if you're using 3 digesters, you could free up capacity on one of those digesters. Full disclaimer, I believe SVCW typically only uses 2 of their digesters for full flow. I'm conscious of the fact that Teresa is on this call and she will correct me if I'm making any erroneous statements about the plant. But the visual still holds here. You could take out a third of your digester capacity. And that doesn't necessarily mean you'd want to get rid of all this tankage, but this is now tankage that in an arid California environment, you could maybe think about repurposing for things like water reuse, for example, which is a growing need in our area. Putting some numbers on the energy balance, the energy requirement, and these numbers are in kilowatt hours per cubic meter, I apologize, but the total energy requirement for this system at Kotiga Center, at SVCW, sorry, I misspoke, is about a 1/4 kilowatt-hour per cubic meter. Now, the energy content of the biogas that's produced in this system, when you add up what's dissolved in the effluent and what's coming out in a gaseous form, from what we measured, and I'll talk about this nuance in a bit. What we measured with our instruments, the electrical energy potential of that total biogas is larger than what we need to operate the system. So you'd have a surplus of about a little bit over 1/10 of a kilowatt-hour per cubic meter, which means your secondary treatment process would be a net energy producer instead of the big energy consumer that it is typically today. So this is what we got based on just our measurements, our instruments on site. When we did a mass balance of our COD, we measured, what's the total COD that's coming into the system? It's about 550 milligrams per liter. What does that equate to when looking at where the COD is going and what we can account for? We found that we were missing a big chunk. There's about a third of the COD that's coming into the system that we couldn't account for based on what we measured. So what that means is that there's a substantial amount of gaseous COD that we're not measuring in our system, or that we weren't measuring it at the time. So that could be a few different factors. It could be instrumentation error. It could be some fugitive emissions, some leaks from our reactor. And of course, that points directly to the challenges or one of the key caveats of greenhouse gas emissions benefits of this kind of system. If we've got fugitive methane emissions, that's not a good thing. So this is something that we've certainly been sleuthing on site to address. But the bigger punchline is when you factor in that, so in a system that is fabricated at full scale with careful attention to making sure that the system is both the instruments are capable of measuring the gas flows accurately and that there are no gas leaks, our energy balance actually looks much more favorable. So here I took a quick moment to translate the numbers into units per million gallons. So if we take what our mass balance indicates is the full biogas production of the system, we actually be able to produce a surplus of about a little bit over 1,300 kilowatt hours per million gallons of wastewater processed. So that's a lot of energy, and that's just the electric energy. There would also be about almost 2,500 kilowatt hours per million gallons of heat energy that would be available for processes like potentially sludge drying or other process heat needs that you might have at a treatment. So we know of no other technology in the world that has demonstrated this kind of energy potential on secondary treatment alone. So basically what this means is you could have a wastewater treatment plant be a renewable energy power plant without having to import high strength organics from other places. So we have examples like East Bay Mud right now that imports high strength organic waste and is able to export renewable power to the grid, but they're not able to do that just based on their wastewater alone. Here you could have a system in which you are producing a surplus power from your wastewater alone, and if you remember that spare digester capacity that you'd be unlocking because you're producing fewer solids, you could import further high strength waste, help the state of California achieve its organics diversion targets, its organics landfill diversion targets, and produce even more renewable power. So this is extremely exciting for us. We think we can actually further optimize the energy consumption of the system. Highlighted here in yellow is the consumption of energy for fluidizing the granular activated carbon. Not to dive too much into this graph, but basically we designed the distribution manifold of this system at SVCW conservatively because you want to make sure it works as you're demonstrating at larger and larger scale. You have to induce a certain amount of head loss in the distribution manifold of the fluidized-bed reactor in order to make sure you have an even distribution of flow inside the reactor. You need about 30% of the head loss that's in the GAs, in the granular activated carbon bed. You need to induce that in the distribution manifold. We overshot this quite a bit, which means that 57% of energy loss that you see in the distribution manifold, plus the 18% in the check valve, we could optimize the hydraulics there to make the system even more energy efficient. So we think that there actually is even more of an energy benefit to be achieved in this system. So now kind of summing up what we've demonstrated or achieved here at the SVCW demonstration. This, as far as we know, is really the first energy positive secondary treatment system that we know of, really building on the success that we had at the Kotiga Center and and enhancing it. That energy positive secondary treatment system would allow an energy positive wastewater treatment plant full on. Meanwhile, you'd reduce the secondary solids production by about 90%, which yields even more energy savings when you think about the trucks that are taken off the road, and energy savings associated with reducing your you could save to about a little bit more than a third of your operational costs based on that, and you would have a lower carbon footprint because you're reducing emissions associated both with energy generation, but also aerobic processes. It's shown now one of the key emissions from aerobic processes is actually nitrous oxide that's produced in the aeration basin. So you wouldn't have nitrous oxide production. You do have methane, so the greenhouse gas benefits are all a function of carefully managing the methane and making sure you don't have any fugitive emissions. So those are the big punchlines from the tests that we've done so far. We're incredibly proud of what we've achieved. And I would be remiss if I didn't kind of highlight our appreciation for SVCW here. This is the East Bay Leadership Council. We talk about leadership. SVCW has really gone above and beyond in terms of showing what leadership from a utility can be. It's research involves some risks. When you write the proposal, you're proposing to do something that you don't exactly know how to do. And a wastewater utility has an obligation to be stewards of ratepayer funds and ratepayer resources. So it takes a great deal of boldness for a utility to take on this kind of project. SVCW did so by pursuing this grant with the California Energy Commission and follow-on grants, and by persevering through a lot of challenges that inevitably come up through these kinds of projects, and doing it in the midst of a pandemic with a massive capital improvement program happening as well. So I can't express enough our appreciation for SVCW, both for their leadership and for the countless members of the staff who have helped us day in, day out, keep things running, get things running and keep things running. But now to talk about some unfinished business about anaerobic secondary treatment. So what are the questions that we still need to take care of before this is ready to take over the world? Dissolved methane management is one of them. So a lot of, as you saw on that methane, on that mass balance that I showed, a meaningful fraction, a large fraction of the biogas that we produce, the methane that we produce, stays dissolved in the water. And that's a problem. So we need to make sure that we extract that methane from the water so that we can use it beneficially and so that it doesn't present a greenhouse gas challenge. We've tested some technologies to do that at the Kodiga Center. So we've got some ideas. I think we still need to show those at scale. We need to kind of demonstrate that that's really feasible. Sulfide management is another issue. So treatment plants have influent sulfate, and it can be seasonal. We're seeing that at SVCW, where there's higher concentrations of sulfate in the winter than there are in the summer. That sulfate produces a lot of challenges. It turns into sulfide, which reduces the methane gas that you're producing, but it also is a corrosive toxic gas in and of itself that needs to be managed. There's different ways to do it that we've been investigating, and I'll talk about a little bit more in a second. But that also presents challenges for disinfection. So sulfides, it turns out, quench our oxide. So if you want to try and disinfect using chlorine, the sulfides will quench the chlorine, so you can't achieve your secondary effluent standards for your coliforms. And it also inhibits UV disinfection. So we need to manage the sulfides in order to make sure we fully achieve the secondary effluent standards. We would also need to manage the sulfides to achieve water reuse standards, which I think, you know, anywhere in California or in the arid West, before a utility wanted to start deploying a system for anaerobic secondary treatment, they would want a hard, fast guarantee that they would be able to achieve water reuse objectives later on with this anaerobic core process. So we still need to demonstrate achievement of water reuse standards. And then there's a broader question about methane utilization. Operate anaerobic digesters at full scale, but I still think at full scale we would need to give some thought to how that methane is managed when you're doubling the production, when you're processing millions of gallons a day of wastewater anaerobically. So your reactors are larger. The potential then to have leaks on those reactors is larger. The need to make sure that you're operating safely and avoiding explosive environments, et cetera, for your personnel and for your neighbors. All of those are questions that need to be thought of and considered carefully. So I showed here, the image here is our miniature flares and sulfide abatements, hydrogen sulfide abatement system for the system at SVCW. Of course, those would be for the biogas. Those would be a lot larger at full scale. And so now talking about some future work to try and address some of those challenges, we have secured with SVCW, so SVCW has secured grants from the U.S. Bureau of Reclamation and the California Water Resources Control Board to test pilot scale technologies for non-potable and potable reuse. So one of the things that we'll be doing there is investigating, trying to find the most low-cost ways to manage sulfide in the SAF-MBR effluent, and then putting together the process trains to achieve the equivalent of full advanced treatment for potable water reuse. So we'll be including reverse osmosis, advanced oxidation, disinfection. And the shipping container that you see there that's been recently installed, that's a technology for nutrient removal that can also double as sulfide management, a membrane aerated biofilm reactor that we're going to be bringing online later this month. So there's a lot of things that are still going on at SVCW. And then thinking a little bit about some paths forward, what would be the next step? What's the next scale? I think that we've demonstrated this system at 24,000 gallons a day. That's a far cry from 12 million or 50 million gallons a day. So I think that there's going to need to be an intermediate scale up going forward to kind of fully suss out the technology before it's ready for prime time. Something on the scale between, I'd say, you know, hundreds of thousands of gallons a day to maybe 1 million gallons. How could that happen? I put together some ideas here. You know, I think one idea would be to convert an existing conventional digester at an existing wastewater treatment plant. The picture you see on the left is actually an inside view of some of the anaerobic digesters at DC Water. These are very large reactors that are quite tall that could potentially work quite well as fluidized bed reactors. And the big advantage there is you'd have some capital cost savings because you've already got a system that's designed to handle methane and the potential corrosive aspects. So that's one idea. And there's excess digester capacity. There's about 2 million. There's excess digester capacity to process about 2 million wet tons per year of food waste in California alone. That's based on a report by CASA. Another option would be a pioneer small to and kind of take the risk to demonstrate this. This is something that Stanford might undertake in a goal of doing decentralized water reuse. So that's another option. And another thought would be an industrial user where the use case makes sense to specifically where the SAF-MBR specifically would meet their needs. And then finally, internationally. So in speaking to my earlier comments about operational experience on how to handle full-scale, high-flow wastewater treatment systems that are anaerobic. There are about 820 full-scale anaerobic wastewater treatment plants in Brazil that are processing the effluent for about 18 million population equivalents. So there is expertise in this globally. Now, those Brazilian treatment plants aren't able to achieve American effluent standards, which is why, and so they use a different technology that's well suited for the tropics, but wouldn't work in our context. But an anaerobic reactor is an anaerobic reactor. And so there is precedent, and there may be, a place like Brazil, for example, might be a place where if they wanted to achieve more stringent effluent standards, they may be particularly well suited with the operational expertise to manage such systems and pioneer. So those were some thoughts on the future, and I'll close off with just a thank you to, of course, first and foremost, the SVCW team. A lot of people have been in. I named some of the SVCW team by name, but there's also the operations staff, the laboratory, maintenance, and warehouse staff who've just been so critical to this project. And on the Stanford team, I'll highlight Chongwon Shin, who Craig already mentioned, who produced a lot of, basically all the graphs that I shared with you today, and has been an amazing researcher, and really spearheaded all of our efforts here. So with that, I'd like to thank you for your time, and leave the floor for Teresa, and maybe hopefully be able to answer some questions afterward.
So thanks, Sebastian, for showing our overview of our treatment plant, because that's probably what I would have shown. So listening to the radio this morning coming in, I heard that it's Random Acts of Kindness Week, and the 17th is Random Acts of Kindness Day. So I'm going to say a lot of kind words about Sebastian and Craig, not just because it's this week, but I give a lot of credit to Sebastian and Craig. They hit up against some walls named Teresa as they were developing this here at SVCW, but persevered, and I'm glad they did, and I'm glad they kept emphasizing the value of what they're doing, because I see it. And that said, I was skeptical at first, and as we all know here, the wastewater professionals tend to be a conservative group of people. We're comprised of engineers, operators, mechanics. We like a lot of safety factors built in. We take our mission as protecting public health, protecting our ratepayers, et cetera. So, we tend to be risk averse. I'm really excited that SVCW is able to find a way to facilitate and create partnerships with universities, researchers, with entrepreneurs, and do it in a way to minimize the risk to the extent that we need to meet our mission, but also to do it in a way to advance the technology and advance the profession. As Bob said, when he graduated from college, and I noted that you didn't say when that was, Bob, but wastewater treatment has not changed for a long time, generations, and it's time. I mean, we have the know-how, we have the spirit and the technology to do it. So whatever we can do to facilitate that partnership and the relationship building with the vast array of people that need to be involved in something like this, I think it's contingent on us as managers, as water stewards to do so. I think Sebastian's first slide showed 13 different organizations that were needed to move this forward to the point where it's at now, including regulators, including the state CEC, universities, private companies, as well as SVCW and Valley Water. So, I think this is a good example of something that is really important to do. And when Bob called me and asked me if I would talk about this, it was an easy yes, because I'm really passionate about this. I'm really passionate about looking and working with innovative technologies and trialing them for wastewater treatment. I mean, currently we have probably 6 pieces of, whether it's equipment or treatment processes, currently being tested on site here at SVCW. We're working with the nation of Denmark that have come forth with several new treatment processes that we're using here successfully now. So it got me thinking, so what makes SVCW different than maybe some other agencies in California? And while I don't know the answer to that, one thing that came to mind is that the entire management team at SVCW came from private industry. So we weren't raised in the public arena. We were raised in the private arena, and I think that brings with it a little different mindset, a little bit not so much in taking on more risk, but looking at proposals in a different way, in a different context. So maybe that's something. The other thing, in preparation for this meeting today, I went and talked to our operations director and our chief operations officer, our COO, and I proposed this scenario. A researcher from a university comes to you with this great idea and says, hey, can I use some space on your treatment plant? Can I take some of your wastewater? Can I use some lab space, to prove out my idea? And I just asked him, what would be your response? And as expected, they said, well, I would want to know more. I would want to hear more about what the idea is, see if it's, completely out of the realm of possibility, or, does it have potential? But I also want to know, what's it going to take from our staff time? Or are you going to require money and, laboratory and operation staff, et cetera? So, and I know Sebastian and Craig understand what questions need to be answered by agency, and they're really good at doing that. So, it's both entities, in this case, both entities meeting halfway and understanding each other's needs and requirements, and understanding possibilities. So just starting the dialogue is obviously number one. Not shutting the door to somebody when they come forth and ask us, hey, what do you think about this? Well, let me learn more. Keeping that open mind, rather than, no, don't have any time. No, we're slammed. No, we got almost $1 billion of construction going on. There could be room for having that conversation. And I hope that, this successful example, as well as, my preaching to the choir as much as possible, can start to open minds and doors a little bit more. Let's see, the other thing I wanted to note is, what's mostly critical to us right now, and Bob and Sebastian both alluded to this, energy costs are a big factor for wastewater treatment. But coming right upside along that is chemical costs and solids disposal costs. So those 3 things are our biggest, besides staffing, are our biggest costs and our biggest unknowns and most volatile from a expense standpoint. So as much as we can even out chemicals, solid disposal, and energy, which SAF-MBR, hits on all 3 of those, I think that's just fantastic. So that's all I wanted to say at this point, if there's any questions or anything like that.
So Natalie's question has to do with the impact on nutrients, native nutrients, that nitrogen, phosphorus, for example.
Yeah, nutrient removal is absolutely, and I was remiss in not putting it on the unfinished business, listing it on unfinished business. It's absolutely a key concern. A little bit less so for the moment, I should say. To date, been given a pass on nutrient regulation. Who knows how long that will last? We are absolutely thinking about nutrient recovery. So first off the bat, the anaerobic process does not remove the nutrients at all. So every pound of nitrogen that comes into the system comes out the other end as ammonia. And there's potentially a little bit of removal of phosphorus, but really not much. So we need to come up with solutions. One of those is that one option, for example, is the membrane aerated biofilm reactor that we're going to start testing next month. So you could have a follow-on process and look at technologies where ideally you wouldn't go through full nitrification, denitrification, because that would eliminate a lot of the benefits of an anaerobic system. But there's so many innovative new processes for nutrient removal, like the MABR, or for shortcut nitrogen removal, where you could do partial nitrification and denitrification. Craig has done some really innovative work on a process called CAN-DO in close collaboration with Gary in his time at Delta Diablo. So there's a variety of different alternatives we're looking at, and we're also looking at it with the nutrient recovery lens. So one option would be you can actually optimize the pH and take the ammonia-rich water and send it to reverse osmosis. And then you actually concentrate the ammonia in the concentrate, which makes it a lot more readily recovered to use it as a valuable resource, as opposed to just trying to send it back in the sky. We use a lot of energy to make ammonia for fertilizer, and it's kind of a shame that our current process is to use a lot of energy to send that ammonia right back into the sky. So there's a variety of different approaches that we've looked at. I know I didn't talk too much about phosphorus. I'll admit that I have not yet investigated a lot on phosphorus removal downstream of this process. That's territory we need to investigate. I'm seeing another question in the chat. This process, everything we've done is at ambient temperature, and so the temperature goes down. So we've had great performance in the summer months. In the winter months, I believe our COD in recent weeks has been, our effluent CODs has been a little bit higher at 40 or 45, but still excellent treatment even in the colder weather of California. We'd have to investigate. It'd be interesting to see how the system would perform, say, in Michigan. But initial tests of the SAF-MBR in South Korea, the water temperature went down to I think it was the mid-40s Fahrenheit, and they were still able to achieve US effluent standards there.
Sebastian, did you happen to see the question in the chat that Jean-Marc put in, asking about expanding research to include nutrient removal?
Yeah, I think we are interested in, so looking at nutrient removal downstream of SAF-MBR, that's something that we talked about. Looking at it sort of independently with different treatment processes, because Kodiga Center is thinking about a lot of things in addition to the SAF-MBR. And there's a couple of things we've looked at. So Craig has worked a lot on CAN-DO, as I just alluded to, which is a way to take the nitrogen and turn it into nitrous oxide, and then nitrous oxide is a booster that actually turbocharges your combined heat and power plant for your wastewater treatment plant. So I would say we don't tend to think so much about nutrient removal as we do about nutrient recovery, or about trying to extract the resource value of those nutrients.
So just say a few words about that. I did mention struvite before, which we've always thought of that as kind of a nuisance compound at wastewater treatment plants. And then some have succeeded in using it as a fertilizer, but it's really as a fire retardant, where the value would really be great. Actually, when we've done this analysis, if anyone's interested in this paper that we published in Green Chemistry, I'd be happy to share that with anyone in the group, where we did an analysis to look at the economic value of struvite when it's used as a fire retardant. And it's second only to the clean water in terms of resource value. It's actually quite a valuable application for the struvite. And it would get rid of nitrogen and phosphorus, I guess, get rid of. It actually valorizes nitrogen and phosphorus.
It's getting close. And so before I close this out, does anybody else have any questions? They can just jump in if they have any questions to our speakers.
So this is Gary. I was Craig and Sebastian. Are you guys willing to share your slides, and you can send them to Lindy so that we can post them on the East Bay Leadership website for everybody in attendance?
Sure.
Thank you, because some have asked that that be done. So thank you, both of you. So here's some ideas. First of all, as time has gone on, Gary and I, for sure, and maybe others, have viewed the value of this task force as educational, as well as sometimes leading to advocacy. Well, today's program is clearly educational, and there is some advocacy associated with it, but it, because there's still a lot of work to be done for the SAF-MBR to get into, I'll just call it the public domain for commercial applications. The performance at Silicon Valley was great, but as Teresa indicated, there are a lot of wastewater professionals, managers, engineers are from Missouri. They want to see more. So the challenge is to see more, not only of all the good work that they're doing at Stanford, but just to advance the knowledge about the performance of SAF-MBR at different applications. So the question back to the audience, those of you who are in positions of making decisions about designs, process design, applications, further research, please consider the need, the desire to expand knowledge, not only at SAF-MBR, but some of the other technologies that are out there. I note with pride that we have here in the Bay Area 3 of the top 10 renowned graduate programs in civil and environmental engineering, environment, Stanford, Cal, and Davis, all of which are about 50 miles away from here in Walnut Creek. So we're the center of the world, best thinking. But are we using that? So the innovative thinking that is coming out of these institutions is marvelous. And we need to reach out and make available our knowledge, our influence, our thinking to advance these ideas and to prove them out. Because so I'm an old guy. I think that that's what we should be doing. I think that the industry should be looking for innovative ideas, wherever they may come from, and try to see how they apply to better the job that we've already been done. Yes, so aerobic treatment is old. It's 50 years old or whatever, but it has done a damn good job of cleaning up the waters of the bay. And we can't let loose of that. We've got to make it better. And these ideas help us along the way. So I'm sure that, that hopefully some of you that are in the audience will start thinking about that as you're preparing your budgets and your management strategies. Make yourselves available to these innovative thinkers at these institutions. And certainly you can get in touch with Craig or Sebastian as to what they're working on directly, but there are others that are out there, as well as what some of the private companies might be doing on their own. So anyway, that's my pitch. So thank you, Craig. Thank you, Sebastian. Go have a good dinner now. And thank you, Teresa, for your comments. Appreciate it all. So with that, I think it's the area's time. So turn it back to you, Gary.
Thanks, Bob. That's a great presentation. Thank you, guys. Sebastian, I looked up on the computer. You are 6,000 miles away. And so thanks for joining us. And Craig, I am so delighted to see a slide now that poses that question, is heat our friend? You and I have been talking about that for about a decade. And so thank you for that. Please join us next month. As I mentioned, we're going to review at the state level what our legislature is involved in as it relates to water. And we have Assembly Person Rebecca Bauer-Cahan is going to join us. She's new to the Committee on Water, Parks, and Wildlife. And so we look forward to that. Thank you very much. Have a good day.
Thank you for organizing this, Bob. Bye, everyone.
Bye, everybody. Thank you.